It's okay.
Oh,
It is. It's okay.
okay, it is doubled because I think the correct one as well.
Okay, that's fine. Don't worry about it. It will cause some confusion, but it's okay. Okay, so let's get started. Good. Okay. All right. So today we are going to continue our discussion from last time, which was on file systems. Okay. Last class we talked about NFS, Network File System, which, as I said, is a very popular client-server file system. We talked about NFS. We talked about how it does caching, cache consistency, and so on. And today we are going to look at more advanced distributed file systems, more newer distributed file systems that are used. Some of them are used in industry and some are used for research purposes. We'll also look at Hadoop file system, HDFS among one of the many. Okay, so let's start with the first one, which is called Coda. This is actually not a new file system. It was designed in the late 80s or 90s, so it's almost 40 years old. But it was an interesting one, and it differed significantly from NFS in how in basically its goals. Okay, in particular, Coda was a file system. It was a research file system. It was developed at Carnegie Mellon University. Okay, and it was designed largely for mobile devices. So this was at a time when laptops were just about being thought of. It was not even a common case. But what the designers of Coda felt was when you have mobile devices, they will look very different in terms of their availability from desktops. Okay? Desktops are typically on, they're plugged in, they're connected to the network. But when you have laptops, you may be using the laptop, then you close the laptop, it goes to sleep, and you go somewhere while with the laptop, it's disconnected from the network while that's happening, or you may take it on the plane. It does not have network connectivity and so on. And if these types of clients want to access files on a distributed file system, how should that actually be done? Okay, so this environment is called weakly connected environment. A weakly connected environment is one where devices may get disconnected from the network for a small or arbitrary periods of time. Okay, and laptops or mobile devices are a good example when you are, let's say, using Wi-Fi and things of that sort. The network, the device goes from one network to the other. It may be disconnected when it's in transit or being taken to another location and so on. Okay, and you still want the ability to work with a file server and get files and so on. Okay, so then the question is, how are we going to make sure you can access data that's stored on the file server while you're disconnected? How can we make sure the data is consistent? Something may change on the file server because another client is accessing the file, and then you are on a client. So you may not be able to get notifications from the server while you're disconnected. How do you handle all of this is what Coda tried to do. Okay? None of these issues were relevant in the NFS case because NFS used a traditional local area network with desktop-like machines where the assumption was they're largely connected to a wired network and are generally available to the server, so they could talk to the server. Here, the assumptions are completely different. So this is what Coda is about. And we'll talk about what it did, and then later on I'll explain how this environment, although the system is now 40 years old, has actually not been used, but the ideas live on in terms of what we have today in cloud storage. Okay? OneDrive, Google Drive, Dropbox, they all took some of these ideas and have implemented it, which is why this is still a good system to learn, okay, in terms of what it did and so on. Okay, so let's start with some basics, and then I'm going to explain some of the more interesting ideas that are in Coda. So first thing is, in Coda, you can have multiple servers. In NFS case, we only looked at scenarios where there's one server and a set of clients connected to them. Of course, can be other NFS servers that are independent. Okay? You can have arbitrary number of independent servers. In the case of Coda, the system itself can have multiple file servers. Okay? So you can have n file servers. These file servers can replicate the files. Okay? So the files are no longer on any one machine. They can be replicated that way. Even if some file servers go down, the others can continue to provide service. So that's the first thing. Okay? So you will see here that there are two file servers. Each file is actually, in this case, replicated across these file servers. And what you have in terms of replication is you have this concept of a volume, which is essentially a set of directories. Okay? A volume consists of a set of directories that are shared with clients. So your volumes are essentially replicated across several servers. Each volume has an ID, so you can track which volume it is, what server it is on, and so on. Okay? So keep that in mind. Okay? You don't need to know any more details here other than multiple servers, files, and volumes are replicated across servers. Okay? Now, when a client tries to write to a file, client modifies a file. Okay? Let's say you open a file in an editor, you make some changes, and you hit save. That's a write to a file. You updated the file. Okay? In this case, okay, the client is basically going to have to send that file to all the replicas. Okay? If there are, in this case, there are 3 replicas. Okay? So S1, S2, and S3. Okay? Your general idea is all writes have to be sent to all the replicas because the file has to be consistent across all the servers. Okay? So every write has to be sent to all the replicas so that you have the same copy of the file on all the servers. That's the general assumption. Okay? Now, the way you do this, you send the writes and each file has a version number. So every time there's an update to the file, you will increment the version. Okay? Now, it may so happen, as is shown in this example, that server 3 might get disconnected from servers 1 and 2. Okay? This is not the device getting disconnected. We'll talk about laptops getting disconnected. Here, let's say the network itself gets partitioned, breaks into 2. So S1 and S2 are on one side of the network. There's one client accessing files on those servers, and there's client B and server S3 on the other side. So network is now partitioned into 2 parts. Okay? And there are some servers on one side, some servers on the other. Okay? As far as Coda is concerned, clients can continue to access their files so long as there's at least one file server they can access. Okay? So neither client A nor client B will see any disruption, even though there's a network partition, because each of them can at least access one server, and we're assuming the files are replicated on also. So all of the files still remain accessible. Okay? Now let's take a scenario where client A and B are modifying the same file. Okay? Now the network has become partitioned. Okay? So A goes and modifies that file. B can also go and modify the files. A's changes are only going to be seen at server S1 and S2 because A cannot send those changes to S3 because S3 is not reachable. Okay? Disconnected from S1 and S2. B can also make changes to that exact file, and its changes are only going to be seen at S2 but not S1 and S3. Okay? Is that clear? Okay? Now, when the network reconnects, okay, you will have to figure out what files changed and resynchronize the servers. Okay? If some set of files changed on S1 and S2, but not on S3, S1 and S2 can simply send the updates, and here are some files that change. You don't have those changes, and send them to S. If some files changed on S3, but they didn't change on S1 and S2, S3 can send those changes and resynchronize, and all is good. Now, if the same file is changed both at S1 and S2 as well as S3, you are going to have a write-write conflict. Okay? Because you can't simply send those changes or override those changes because some 2 different set of users have modified the same file. So you will have to essentially flag this as a conflict, and then it's up to the user to essentially figure out what to do. It's exactly like if 2 users have checked out the same file from, let's say, a source repository like GitHub or something like that. You make changes and you cause a conflict, then it's the user is going to have to figure out what the changes were, merge them, or throw away one of the files. Exactly the same process has to happen here. Okay? This is before source code control was ever designed, the file system itself is providing that functionality automatically. Okay? Now, the question is, how are you going to know that there is a write conflict? The way you are going to do this is essentially, as I said, each file has a version number. Every time you update it, you keep track of that version number. So for example, let's say that this file that we were talking about starts with version 1. Okay? Every server in the system has version 1 of this file. Okay? At this point, the network gets disconnected. Okay? So the version vector is going to look like 111, which means that server 1 has version 1, server 2 has version 1, server 3 has version 1. Okay? Now, if A modifies the file, okay, it is going to send updates to S1 and S2. So on this side of your left side of the partition, the version number looks like 221. Okay? Because these servers know that the change was not sent to S3. So they will believe that S3 still has version 1 of the file, but they now have version 2 of the file. So their version vector on this side is going to look like 221. Okay? On the other side, if the same file is modified, only S3 sees it. It knows that the change was not sent to S1 and S2, okay? Because the network is disconnected. So it will think that the version number is now 112, which means that it has version 2 and it has yet to send that to the other 2 replicas. Okay? Now, when these servers reconnect, you will compare these version vectors. And here you will see that the version vector will tell you the version was changed, the file was changed on both sides of the partition. Okay? So you cannot actually override the file. Okay? If your vector is strictly greater than the other side vector, you know that you have changes that others don't, so you can actually update it. Okay? So this is clearly telling you there's a write conflict. So you will flag this and let the user deal with it. Okay? So now it's user's job to figure this out. Okay? So this is how Coda handles issues at the server level. Okay? Of course, there are going to be issues now, because we'll talk about what happens when clients disconnect and make changes and so on. Is this clear? Okay. All right. So now let's look at a laptop, which is really what we are worried about in Coda. That's basically going to be working with a server. Okay. So long as that laptop device or a mobile device is connected to the network, it can access the server normally, like any other client. Anytime it needs a file, it will use RPC or some other mechanism to access it. Anytime you make a user changes the file locally, is going to tell the server or all the replicas of server, not even one, all the replicas. Okay? Now, when the machine disconnects from the network, okay, let's say that you go to a location where there's no network. Maybe you're taking a bus home and you're working on the bus, or you take a plane and there's no network on the plane. You cannot access the server in this case. Okay, server is disconnected. So now the client has disconnected from the network. Okay? The previous case, the two groups of servers got disconnected from one another, and the client has disconnected from the server. So what should happen in this case? Okay? What Coda's philosophy is that you should try to cache copies of files that the client is likely to access on the device. Okay? So now when the client disconnects, okay, if you cache the right copies, the files are still now on your local disk in your cache. So your applications can continue to work with those files as if the server had never disconnected at all, because you still have some copy of the file. Okay? So you can make changes locally. Okay? And when you reconnect with the server, you will have the same synchronization protocol. You will ask the server, well, have any files changed, and fetch them down. And then you will see what files change locally and send them. And of course, if there's a conflict like before, you will flag. But if some other user modified the same file while you are disconnected, you will have to flag a conflict and do manual reconciliation. Okay? So that's the basic idea. So you will see that the client device at any instant can be in one of 3 states. One is called hoarding. Hoarding is the process of downloading files to your device into your local cache, so you can hoard them locally. Okay? And so if you get disconnected at any instant, you still have some files on your server. Okay? Now, it's clear that you can't store all the files on the server locally. You just don't have enough disk space. But the idea is, if you know the typical files a user accesses commonly, maybe it's their home directory, or maybe some common files, commonly accessed files from the home directory, you hoard those files. Okay? So you have to make sure that you're getting the right set. Okay? So you could be in holding state when you're connected to the network. Okay? You are just doing hoarding, which is your downloading file. Okay? When you disconnect from the network, okay, you will go into what is called emulation state. Emulation state makes the client pretend like it's connected to the network, but all the files that the client's applications are accessing are actually stored on the local cache. Okay? So you are emulating the presence of a server, even though there isn't. The cache is acting like your server temporarily. Okay? So you can you see all your directories, you see all your files, even though they were supposed to be stored on the server. You can open them, modify them, do whatever you did normally. So users are, if you hold the right set of files, the users see no difference at all. It looks like your files are still there. Nothing has happened. Okay? So you can go off, everything looks like it's all there. You can continue to modify it. So that's in the emulation state. When you reconnect, okay, you go into what is called a reintegration stage. This is where your device and the server are going to talk to one another and try to resynchronize all the files. Any changes that were made locally have to be sent to the server. Any hoarded files that were changed at the server have to be fetched. Okay? So this is essentially reintegration. And once reintegration is done, you pushed all your changes, you'll go back to hoarding state. And you might say, I need to download more files because there was this directory that was not downloaded. User tried to access it, got an error. Of course, any downloaded files you try to access in emulation will still give you an error, okay, because you did not download it. But the next time you can see that and download it. So you'll go back to hoarding state and then you'll cycle between this. Okay? So this was designed in a way where users really do not see any impact of whether they're actually connected to the network or not. So long as the file system is able to hoard the right set of files for each user, it will be different across users based on their access pattern. Okay, everything just looks as is. Nothing looks like when you're disconnected, you can't access your files or anything like that. Okay, is that clear? Yes, question. Okay. Questions: how are write-write conflicts handled in the reintegration stuff? All conflicts that are found by the system have to be handled by the user. The user will be told that this file, it's exactly how Git will give you a conflict. Okay? When you try to merge, or even not merge, but commit and sync, you will see that there is a conflict and the user has to resolve that conflict before that file can actually be committed. Same thing, the user has to resolve and tell Coda that this is the correct merged file or this is the correct version, and that's what you want to use, and then it will be uploaded. Okay? Handled by user, not automated. Okay, so that is Coda. There's one more thing I wanted to say that is interesting in Coda, which we have not seen before, is that it provides transactional semantics, which means that essentially all the operations that are performed on files, okay, they'll almost look like database transactions in that they are serializable. It allows you to figure out which time which file was modified because they are serializable. In case of conflicts, you can use some of this information to help the user say this file was modified at this time, this other file was modified at some other time. So it has transactional semantics that can be used to undo changes if necessary and things of that sort. Okay? So that is not something we have seen in any of the other file systems because they just use standard file system semantics. This one actually gave a little more to the user in terms of transactional semantics. Any questions on Coda before we move on? Okay. So it's an interesting file system, and as you can imagine, okay, the file system doesn't exist, although its code might still be available somewhere. The ideas that it had actually are exactly what you have for cloud storage. Okay. In your cloud storage, the storage server is in the cloud. Your device is the client. Okay. And when you're connected, you can access your cloud files, OneDrive, Google Drive, Dropbox, and so on. Okay. When you disconnect, okay, most intelligent cloud servers are actually going to keep a copy of those files on your device. Okay. Dropbox will put it in a Dropbox folder. And if you have, let's say, Google Drive in offline mode, okay, Google Drive will also cache a copy of it either in your browser cache or on your disk and so on. So you can continue to access your files even though you're disconnected from the server. And when you reconnect, that exact process I talked about will actually occur where you are uploading your changes, downloading from the cloud server, any other changes it has seen, and so on. And if there's a conflict, same thing will happen. you will see two copies of the file saying this was a modified copy by this user, this is modified at this time. You have to then figure out how to merge and reconcile and rewrite it. So all of those ideas still there. Okay. And of course, you can see source code control system adopted similar ideas as well. But even storage systems today use some of them. But this is where they originated for more than 3 or 4 decades. Right? Okay. So we will now talk about, that's one file system we talked about. Right? We are going to see 4 or so today. Okay. The next one is called xFS. Okay. That's a small x, and that x is simply a cross, which is trying to say it's essentially a serverless file system. Okay. And X stands for no server. Okay. So very different architecture, as we'll see. So essentially, this is like a serverless. It's not really a peer-to-peer file system. Serverless doesn't mean it's P2P. Serverless means it's a distributed file system where there is no single machine that's called the server. All nodes in the system are going to participate in providing file service in some shape or form. Okay? So that's the idea. So this is basically a decentralized file system where every node participates in the environment. Okay? And so X here essentially stands for no server. And the idea is all distributed file systems we've seen so far, and some more that we will see, use a client-server architecture. There are servers, okay, maybe more than one, many servers that store your data. And there are clients that access data. Clients might cache data, but the master copy is always on server. Okay? So if you remove this distinction, okay, you can say clients have lots of disk space. Okay? You might have whatever, half a terabyte or a terabyte disk space. So why not use all the disk space on all the machines to construct one large logical file system? Okay? In this case, there are no servers. Every machine provides some functionality of the overall server. It will provide some storage space. It will provide some additional processing to access data and so on and so forth. Okay? So essentially, in this case, any data can be stored anywhere. Okay? You'll have a set of machines that collectively provide our distributed file system. So some of them will store data, some of them will store metadata, and we'll see how all of this works. Okay? So that is xFS, but I have to talk about two concepts before we get to how xFS itself works. The first concept is it basically uses this notion of RAID or redundant array of independent disks, okay? Because when you have lots of machines that are participating, you have to ask what happens if a client crashes. Okay? Will some of those files become unavailable? Not a good idea, right? If you stored some files on a machine dies or the user just disconnects it, you don't want the files to disappear. You still want the files to be available. How are we going to provide reliable access to files when some machines go down? Okay? So that requires us to essentially use RAID and some technique called striping, which I'm going to introduce. And then the second is essentially, how am I going to provide fast access to files? So you have a large cooperative cache. Okay? Rather than in a central server, there's one cache at the server that's allowing you to accelerate your read request. In this case, it's cooperative caching. When we talked about web caching, I introduced this concept of a cooperative cache where each machine has a small cache. So if your machine does not have the requested data, you ask nearby machines. So the caches are working with one another to serve read or write requests. Okay? Same concept is used here, which is a centralized, not centralized, a decentralized cooperative cache. Okay? But let me first talk about what RAID is, and then we'll come back to this. Okay? So let's first try to even ask, why do we need to provide reliability? Okay? So this is now taking a step back from xFS. I'm going to give you some general background, and then we'll bring it back to xFS. Okay? So let's just take, for just a second, not xFS, but let's just take a server with many disks in. Okay? Single server, many disks. Okay? Now it just turns out that if you take any one disk and you look at the manual on that disk, it might say that the lifetime of that disk is around 50,000 hours, which is many years. Okay? 50,000, 100,000 hours. Typically, all of these disks or products you buy come with some notion of what is called mean time to failure. Okay? MTTF. Okay? That's called mean time to failure, which is mentioned here. Okay? That typically means what is the average time this think will last before it dies. Okay? Discs typically have that you buy typically have lifetimes of few years, 5-6 years. Okay? So if you buy 10 discs, okay, if you have one disc, you should expect that it's going to be there for about 6 years before it fails. Okay? But now what happens if you have lots of discs? Okay? Now discs, just because you have many discs doesn't mean they will all last for 6 years. On average, components can fail much before 6 years. That's just the average. Okay? So these components can start failing, and in fact, they might start failing independently. Okay? Because if you remember, when I talked about reliability, okay, long time back, I said if there are n components in the system, if P is the probability that a component can fail independently, the probability of any one failure is 1 minus P to the power n. Okay? Because you have to assume that none of them fail, and then 1 minus that is probability that some component. As n goes to infinity, the P to the n terms goes to 0. So the probability that there's going to be a failure in the system starts approaching 1. Okay? That's the same concept mentioned here, saying if one disk has 50,000 hours lifetime, okay, if I have 70 disks in my system, I should expect to see a failure every 700 hours, okay, which is almost once a month. Okay? If I have more than disks, I might see failures every week. Okay? So what this is saying is when you have a large number of components, okay, the probability that any one of them fail for any number of reasons keeps on growing and it starts approaching. Okay? So if you simply take a bunch of disks, okay, and start storing files on them, okay, and you have a large number of disks and lots of files, some of your files might become unavailable if the disk fails. Okay? So essentially, large file servers, which are many disks and have no redundancy in those disks, okay, are not going to be reliable, okay, because the chances of failure are just too high. As you go, even with 70, 100 disks, which is not a lot if you think about it. We're not talking about tens of thousands of disks. We're just talking about even 20, 30, 50, 100 disks. Okay, you'll start seeing failures. Okay? So you need to ensure that you can somehow overcome this issue of failures. Okay? So to make your server reliable, you have to put redundancy in it. Okay? So we'll look at how do you do this. Okay? And here by array, I mean a disk array. A disk array is just an array of disks. Okay? So just think of it as there are n disks in my system, and so that's my disk array. Right? So so here is where we will bring this idea of RAID, which is a redundant array of independent disks. So we'll make the array redundant rather than not non-redundant. Non-redundant means if a disk fails, it's gone. Okay? So before I talk about how RAID works, I'm going to introduce a concept to you, which is called striping. Okay? File striping. So what does striping mean? Okay? Typically, when you have multiple disks in your system and you want to store a file, you are going to store a file on a single disk. Okay? So let's say you have 2 disks in your system. You create one volume and you create another volume, and they have a set of directories. You put a file in one directory, it will go on one disk or the other. Okay? Now, when you have striping, you are no longer going to do it. You are going to take a file. Okay? You are going to chop it up into blocks. Okay? Every file has n blocks. Okay? And you are going to put these blocks on these disks in round robin fashion. You are distributing the data of a file across all the disks in the system. Okay? It's the exact opposite of what you normally do, where all the blocks of the file sit on the same disk. Okay? Instead of keeping a file on one disk, I'm keeping not copies of the file, but blocks of the file. Not that the file is replicated. I just chopped it up into smaller pieces. I kept block 1 on disk 1, block 2 on disk 2, block 3 on disk 3. You do this, you round robin, and you just spread all of your data. Okay? This is called striping. Okay? I striped my data across all the disks in the system. Is that clear? Okay. So reason is what, not reason. The question is, what does this give us? Why would we ever want to do this? Okay? Let's not think about the failure case yet. We have not done any redundancy. Let's just say I give you an array of disks rather than putting some files on disk 1, some on disk 2, some on disk 3. You take every file in the system, you chop it up into smaller blocks, and you stripe them across the disk. Okay? So what might be some advantages of doing this? Or why would you even consider doing this? Yes. Okay, so you effectively create one large logical disk. So you will basically have a logical disk. Okay? But remember that if you did not do striping, you still have n disks. So it's not that you increase the storage space. Okay? Storage space still the same. So instead of the user seeing n disks, they see one disk. That's true. Okay? Is that an advantage? I didn't increase the storage space yet. Okay, so, but you're right. But that's not necessarily an advantage yet.
Even if one disk fails, we'll still have some content of the file available to the other disk.
Okay, so question is, so let's not talk about failure yet, but what you just said is if one disk fail, okay, so you'll still have contents of that file on another disk. That is true, but is that useful? Let's say you wrote some code, every third line has disappeared. Okay, so I don't know if that is useful or not. Maybe you have to think about that. But you're right, only 1/n of the data is going to disappear of each file. Okay? Yes, question. No, not question, comment. Yeah.
That mean that if each block of the file is on all of the disks, they respond to the block of the file and when you get a file.
Yes. So as you are pointing out, what we have just done by striping is we parallelize the storage. Okay? If I have to fetch if I put the entire file on one disk and I have to fetch n blocks, I have to send n requests. All of the requests go to the same disk and they are getting fetched sequential. Okay, because disk is a sequential, it's going to get one block at a time. Now I put my blocks across all the disks. So if I have to fetch n blocks, I'm sending this request on all the disks are working. Okay? So each request is n times the throughput of a single disk. Okay? So I parallelized my IOs. IOs will be much faster in this case than a single disk. Okay? Of single disk. Okay? Not that if all the disks were busy, the overall throughput is still going to be the same. Okay? But for any one request, I could parallel. The other thing you have done here is we have load balanced. Okay? Remember the distributed systems class, right? So if you just kept files on arbitrary disks, you don't know when you create the file how popular it's going to be. Some files might be very popular, might get lots of requests. Other files may not. So there's no guarantee that the disks will be seeing the same load just because I put individual files on separate disks. Some disks might be overloaded. Some disks might be underloaded. Even though they have a lot of content, nobody is accessing those files. Okay? But when I stripe the files, the system is load balanced automatically. Because every request is by definition going to go and hit all the files, all the disks rather. Okay? So it load balanced you without doing anything extra because I didn't need to know what the access pattern was a priori to put the files on some disk so that I balance the load. I just striped it and I got load balancing. I got parallel access as well. Okay? So I could speed up my reads and I have load balances. These are advantages of striping. Okay? But remember what I said on the previous slide was as you have multiple disks, the chances of a failure go up. Okay? So now if a disk fails, okay, the content, whatever blocks you stored on that disk is become unavailable. Okay? So this actually is a disadvantage, although you said it was an advantage, because in the previous case, okay, if I store files on separate disks, okay, if a disk fails, 1/n of my files become unavailable, but the rest of the files are still accessible. Right? Because the other disks are still working, the files are. In this case, okay, if a disk fails, 1/n of every file becomes unavailable. Which may mean that no file is available because 1/n of the content of every file has disappeared. Okay? So in this case, the impact of failure might actually be larger rather than less because I have basically now compromised some content from every file by making it available. Okay? So if you don't have redundancy, this is going to be a problem because you'll say disk striping is great for performance reasons. So I get load balance system, I get better faster IO, but from a failure perspective, it's actually bad because all my content is now at risk. Okay? Not just the files that are stored on that one disk. So we need to now add redundancy to the system to keep all the advantages of striping, but remove this one disadvantage which says when failures are common, this is going to be a problem for the disk array because a lot of files might just disappear. Not a lot, all the files might just disappear. Okay? All right. So that's the background. Now let's see how to add redundancy to striping. Okay, to get this. So striping, by the way, is called RAID levels. RAIDs have levels. Okay? Levels say how much redundancy is there. Level 0 means no redundancy. So RAID level 0 is simply a large logical disk because you created an array and you did striping. So you see this entire array as one big disk. Okay? I don't see any individual disks anymore because I just see one big disk. I see the total storage. Okay? But there's no redundancy. So level 0 means no redundancy at all. Okay? You can do level 0, but you take a chance. So now we'll start adding redundancy. Okay? So RAID level 1, what does that do? Okay? That's called mirroring. Okay? That's shown here. What does mirroring do? For every disk in the system, I'm going to create a backup disk. Okay? So essentially, every block is stored in two places. Okay? It's stored on a primary disk, is stored on a secondary disk. Okay? So now if a disk fails, I can go to the backup disk and fetch that block. Okay? So I made 2 copies of everything. Okay? So that's RAID level 1. Very simple. It's called mirroring. Okay? Every disk needs a backup disk. So if I have n disks in the system, okay, I essentially have n over 2 disks of effective capacity because the other half of the capacity is serving as backup. Okay? So I have 10 disks. I'll basically have first 5 disks as my primary. The other 5 disks are my backup. So I essentially see a system with 5 disk effective capacity because the other 5 are basically a backup. And every time I write a block, I have to write it to 2 locations because I'm going to still stripe, but I'm striping across the first 5 disks. And then the other 5 disks are repeating that and they're striping across those 5 disks. So I'm going to write a block in both the primary and its secondary location. Okay? So this has taken care of failures. Okay? Because if one disk fails, there's a backup disk. Okay? But it is, of course, a problem because now your capacity is dropped in half. Or in other words, you need a certain capacity. You have to buy twice as much disks to meet that capacity. So I doubled my system hardware cost of storage. Okay? So you might say, I don't want to double my cost. That's just too much of a price to pay. So can we do better? Okay? So mirroring is the basic level of redundancy. You're just going to make duplicate copies. Okay? So that's RAID level 1. We are going to skip a couple RAID levels. We're going to skip over 2 and go directly to essentially RAID level 4. Okay? So, or rather RAID level 5. So let me explain 4 first before we actually get to 5, because I need to explain how we are going to keep redundant copies without actually having 100% overhead. Okay? We are going to use a very simple idea of XOR operations. I don't know if all of you at least know what XOR is, right? So essentially, what we are going to do is use the following property. Okay? If you take 2 bits, let's call these 2 bits A and B. If you do A XOR B, you get a product C. Okay? If you look at the XOR table, okay, and then you can actually verify literally that if I give you A and the output C and I XOR them together, I get back B. Okay? And if I take B and C, if I XOR them together, I get back A. Okay? So that's a property of XOR. So if you have A and B and I do A XOR B, I get C. If I can substitute C for A or B, and I'll get the one that I'm missing. Okay? This is the property of XOR we are going to use. So what we are now going to do is we'll take not one block, but a collection of blocks, n blocks. Okay? We are going to XOR them together. Okay? And I'm going to get a new block, which is called a parity block. Okay? Is this clear, what I just said? So what do you mean by XOR a block? I take the first bit of the first block, second bit, third bit, I XOR them. I take the second bit, so I take each bit of each block, I XOR them. So I now have a bit for each of the first bits, of another bit for each of the second bit, and so on. So essentially, here is an example. Okay, I have 4 disks, D0, D1, D2, D3, or in this case, they're blocks. I XOR them, I get a new block called a parity block. Okay? Now, if any of these disks fails, okay, let's say in this case, D0 is gone. Okay? So all the blocks on D0 are gone. Okay? But I still have my parity block. Okay? What I can do to reconstruct D0 is I can take D1, D2, D3, and P. If I XOR them together, I get back D0 because of the property of XOR. Is this clear, what I just said? Okay? You have to actually look at an XOR table and convince yourself this is true. And you will find if you just take A and B as 2 bits and do this, you will convince yourself that's actually true. Okay? All right. So what will we do with this? Okay. So long as you have no failures. Every time I try to write a block, I am going to compute a new parity, okay, and I'm going to store it. Okay? And if any of the disk fails, what I'll do is and if the user wants to access a block stored on that disk, I'm going to get what's called a parity group. Parity group is a set of blocks and the parity block that were computed earlier. I'm going to get all of the ones available. I'm going to do an XOR on the fly, and I'm going to reconstruct the block that was stored on that disk, even though I don't have it anymore. Okay, so I just got back that data magically because I stored an extra parity. Okay, yes. Okay. Question: what if the parity block fails? So in this case, RAID is designed to handle one failure at a time. Okay? If you want two failures, you need more complex schemes. Okay? So whatever I talked about, even mirroring, same question. You could have said, what if the main disk and the mirror fails? Data is lost. Okay? So this is designed to withstand one disk failure at a time. Okay? If you have two disk failures, you need more complex coding schemes. These are the simplest ones. Okay? So we talked like replication. Now we talked about the blocks. Okay? So here is an example, okay, where your D0, D1, D2, D3. These are 4 blocks of a file. I compute a parity block. I keep it here. Okay, then I'm continuing to stripe, so I put the next 4 blocks there, compute a parity block, there's another parity block there. Okay? So I'll continue to do this, still striping, but then one disk is storing extra information, parity. Yes, question. Okay, good question. What happens if one of the blocks changes because of a write? So I computed this file, okay, or not computed, I stored this file. I open this file in my editor, I make some changes, I store it back. Okay? But let's say I only change the first line of the file. So this block is actually the one that I changed. Okay? How do I store that? I can't just go and overwrite this block. Okay? What I have to do is to write this block, I have to first read the entire parity group. I have to get D1, D2, D3 out. Okay? I take the new version of D0, I recompute the parity that way, okay? And I write it back. So essentially every write request, okay, does what is called a read, modify, write cycle. Okay? To do a write, I have to first read the parity information first, not the parity group first. Okay? Then I have to essentially do the modify, which means I recompute the parity. Then I go write the block that changed, I go write the parity. The others have not changed, so I don't have to rewrite them. I just have to read them. Okay? So writes, small writes are expensive. Small writes require n-1 reads. Okay? If n is the size of the parity group, recompute the parity and 2 writes. Okay? So essentially there are n+1 IOs for every write IO. Large writes, not a problem. If all of the blocks changed, I can just recompute the parity. Let's say I change the file completely. Okay? I already have the blocks. I compute the parity and I write. So large writes are not a problem because I just like I recreate a new file, I just compute the parity and I just stripe the new data over. Okay? Small writes are actually expensive in RAID. Okay? This is called RAID 4. Okay? RAID 3 is like this, but it does things at a byte level. Okay? RAID 4 does things at a block level, but they both compute parity. They always have a designated parity disk where this extra information is stored. Okay? And all the other disks are data disks. So there are data disks and a parity disk. And essentially the parity disk stores parity information. The other disk stores data information. Okay? And I'm still using striping. So now I still have all the properties like before. If one disk fails, my data is not gone, just as in mirroring. My hardware cost, extra cost is 1/n, where n is the size of the parity group. Okay? You as a user can configure the size of the parity. You can say, I want the parity group to protect 9 other disks. So then the parity group is 10 size. So there's 1/10 the cost. Or you can say in this case, okay, you have 5 disks, 4 of them are data disk, 1 is the parity disk. So it's 1/5 the cost. So extra cost will depend on the size of my parity group. Okay, is this clear? All right. So we solved one problem, which was we said mirroring is too expensive. We have now a better scheme where I have the same redundancy. Okay? It has actually reduced my hardware cost, but we complicated a few things. Okay? In mirroring, every write was 2 writes, one to the primary, one to the backup. Here, a write, if it's a small write, is n-1 IOs because I have to do a read, modify, write cycle. I have to read the parity group. I have to modify the parity block. I have to write the originally changed block and the parity block. Okay? Large write still okay. Okay? But even with all of that, okay, there is still an issue here. Okay? So let's think about what the write traffic is going to look like. Okay? Let's say I'm making lots of changes to my files. Okay? Every write, okay, if it's a small write, is going to hit one of these disks, okay, depending on which block you change. Okay? Every write always hits the parity disk, because every write always modifies up some parity block. Right? So put another way, okay, the load that is seen by the parity disk, okay, the write load seen by the parity disk is the sum of the write load seen by all the other disks. Okay? Because every one of these writes, okay, also adds up to a write on the parity disk. Okay? So what this is saying is the parity disk here is going to get overloaded, okay, because it sees n times the load of other disks, which is always in the critical path. So every time you're trying to do a write, you have to read that parity. Okay, is that clear? So that's a disadvantage of RAID 3 and RAID 4, because you have a dedicated parity disk, which is good because it is now less expensive than mirroring, but it sees a much higher load. The system can get overloaded. Okay? There's a moderate load. This thing is going to just saturate very quickly, and then you will not be able to write very quickly to the system. So what should we do? Okay, how do you do that? And your duplicate parity, sure. Okay, so you're saying let's duplicate the parity disk itself. You could do that. It's increasing your hardware cost, right? Sure, that's one approach. Yes, you have some other idea. Okay, so you can cycle the parity disk. Okay, so you should ask, why should I store all the parity blocks here? Why should there be a designated parity disk? Why not for the next group, I actually put the parity block on some other disk and so on. Okay, so if I distribute the parity blocks, okay, across multiple disks, then this problem that there's one disk that's seeing all the load goes away. The parity load is also spread across all the disks. The data load is also spread across all the disks. Okay, then I don't have this problem. Okay, I still have my read, modify, write cycle, but at least I didn't make one disk see n times the load of other disks. Okay, so once you do this, okay, you are going to essentially get what is called RAID 5. Okay, you will see in RAID 5 the parity disk is actually no longer a designated disk. You are just cycling through. Okay, so in the first parity group, the fifth one is the parity block. In the second group is the fourth one, third one. So each of them is protecting the other four blocks. So I have distributed my parity across all. Okay, this is called RAID 5. Okay, still very popular approach. If you use any system with multiple disks, it has disk arrays. By default, you should at least do RAID 5. Okay, there is something called RAID 6, which is allowing you to handle multiple disk failures and so on. But the basic level is I should at least protect all my disks by having a parity information in there, and I want to distribute my parity. So this is distributed parity. Okay, yes, your question. Okay. Question is, can a file not be stored as the same disk as the parity? I'm not fully understanding the question, but let me explain. If the file has 10 blocks, okay, so you are going to essentially put the first block in D0, D1, D2, D3, D4, D5, D6, D7, and so on. Okay. So yes, you will have some parity blocks and some data blocks, but what you will not have is the parity group cannot be stored on the same disk. Okay. So essentially, D0, D1, D2, D3, and P are form one parity group. Okay. Those blocks have to be stored on separate disks because you cannot have more than one block of your parity group disappear. Right. So is that clear? So each parity block is protecting 4 other blocks. All of those 4 blocks and the parity have to be stored on separate disks. Okay. The next parity group will also have 4 data blocks and parity. You can put the parity on some other block. It doesn't matter. Okay, because each of them is an independent group. Is that clear? Okay. What other questions do you have? So this is called RAID 5. As I said, it's still very popular. It's used in many contexts. Okay, so large storage systems will all use it. So this is what xFS uses. This is just a little bit of a digression to explain how xFS works, because we're still talking xFS. RAID actually has nothing directly to do with xFS. It was developed as a storage service. Okay, so even a single server system with multiple disks can use RAID. Okay, that's the most common case of RAID. Is I buy a large server, I put 10 disks in it. You should not use them independently, because chances of them are going to fail are high. So you should construct what's a RAID volume on them, so that you keep some extra information. Okay? So typically RAID is used in single server context, but we will see how to use this idea for xFS, which is a distributed file system. So RAID by definition is not distributed across machines. It's just distributing the storage across disks within a single machine. Okay? That's the more common case. Okay, that's the first concept. Okay? So xFS uses software RAID. Okay? What it's going to do is, rather than having n disks on one machine, remember I said it's a distributed file system. Okay? I am going to stripe my data across machines, not across disks within a machine. So if I have n machines, I take a file, I put block 1 on machine 1, block 2 on machine 2, block 3 on machine 3. At some point, I compute a parity block, I store it on yet another machine. Okay? So I'm striping or doing what is called network striping. Network striping is same as disk striping, except that the data is being striped over a network across machines rather than within disks of a same machine. Okay? So it's going to use a network striping mechanism. Okay? It will still have this performance overhead for small writes. I already mentioned that. Okay? And that might be expensive, which is why they put a big cache. Okay? So you always write to the cache, and then the cache can write it in the background. Otherwise, if you wait, you do a small write, you have to wait for n plus 1 IOs to finish before your write comes back. So you will use caching and things like that to compensate. Okay? But that's what xFS is going to use. That's the first concept. It's going to use a software RAID. So it says software RAID because typically if you buy a big server, you will get a hardware card that is designed to just do RAID. So it's going to have specific hardware to do XOR very fast. Yes, because you have hardware to do this, all this parity computation, etc., can be done very quickly. Okay? Here you are distributed, so you can't have a RAID card because you are striping across a network. So you have to do all of this in software. Some machine has to compute the parity, okay, by just doing XOR in code, and then write them all out in different machines. Okay, all right. That's one. The second thing that xFS uses is called log structured file system, which is called LFS. Okay? Again, this concept, just as like RAID, was developed independently. Log structured file system is actually a centralized file system, but xFS uses the log structured idea in it. And we'll first have to understand what is log structured file system before we can see how xFS uses it. Okay? So log structured file system, again, they were developed maybe late 80s, early 90s. Okay? And the idea there was you want to essentially develop a file system that is designed for servers with very big caches. Okay? Because as the size of memory on machines increased, you could put bigger and bigger caches on these file servers just to improve performance. So you don't have to do slower IOs. Okay? But if you put a big cache on a file server, you will see that the traffic that the disk sees is going to be very different than if there was no cache. Okay? So let me give you an example. Okay? Let's say there are 100 requests coming into the file server. Okay? Half of them are reads, half of them are writes. Okay? Just as an example, equal number of reads and writes. Okay? If there was no cache, the disk is going to see 50% reads, 50% writes. Okay? Now let's put a cache on the disk, on the server. Okay? So every request is to first look in the cache. If it's a cache hit, you are done. Okay? There's no IO. You just return the results from the memory cache, and there's no disk IO. Only if there's a cache miss are you going to see a disk IO. Okay? So if you have a big cache and you have good cache hit ratio, most of the reads are going to be absorbed by the cache. Okay? Most of the writes, on the other hand, still have to go to the disk. Okay? Because the cache, it might go to the cache, but the cache has to flush them to the disk because the machine dies, the in-memory cache is gone. Okay? So you to make the data persistent, writes might hit the cache, but they eventually, either to write back or write through caching, they have to propagate to the disk. Okay. So if you now look at the disk traffic after the cache has absorbed some of these requests, what do you think it will look like? It will be mostly writes because most of the reads are now absorbed by the cache. Okay? So you have fundamentally changed the type of traffic the disk is going to see. So there will be a few writes. Those are the not few writes, few reads. Those are mostly the cache misses. Okay? But most of the writes are still trickling down from the cache into the disk. Okay? So that basically led these researchers to ask, how can you think of a file system that is optimized for writes? Because when the cache is put in front, the writes are the common case for the disk. Reads are the uncommon case because reads are mostly getting serviced from the cache. Okay? So log structured file system is highly optimized for write traffic. Okay? So it is not optimized for read traffic. Normal file systems before then, they did not care. IOs were IOs. We didn't care whether the reads or writes. They just went and either read from a block or wrote to a block. In this case, you are going to say, I'm going to optimize for write. Okay? So question is, what can you do? Okay? So the basic idea was, the first thing is to keep in mind is this was designed in the 90s where you still had magnetic disks, okay, which looked like CDs they spun, as opposed to solid state disks that you have today, which just look like USB, there's no moving parts. Okay? So everything I'm going to say has a historical context because some of what I'm going to say does not apply when you have SSDs or solid state disks. Okay? But imagine you have a disk that looks like a CD, which all of you still know what that looks like, right? So CDs, you put them, they spin, okay? And then you have to essentially read or write by moving the needle to the right location on the CD and then read from there. Okay? And typically when a file system stores data, the file blocks are not stored contiguously. Okay? You can store any block anywhere on disk. Okay? So blocks of a file are going to be scattered on, think of a CD platter, they'll be scattered everywhere. They won't be written in a linear chain or anything like that. Okay? So to read a file, okay, not write, but to read a file, you have to first move to the disk head to block 1 while it's spinning. Then you have to move it to block 2. Then you have to move it to block 3. It's not like you move it one end and you contiguously read, because the file is not stored contiguously. Okay? File is stored in different places. Okay? And if you do writes, it's the same thing. Okay? You will put one block somewhere on disk, then you will move the diskette somewhere else, put another block and a third block and so on. Okay? That's what write traffic will look like if you're not storing contiguously. Okay? So the question is, how are you going to optimize write traffic? What you want to do is to minimize disk head movement to maximize throughput. Okay? Because when you move the disk head from one block to the other, you're not reading or writing. You're simply trying to position to the next location, then you read. And you move the diskette to another location, you read from that location and so on. This is called disk seek. You're essentially seeking to the right location. Okay? If you remember any OS, I think you might have looked at what was called scan or elevator algorithm, which was just seeking from one location to the other. Okay? Disk seeks are wasteful. Okay? Because the disk is not doing anything while you're seeking, you're just trying to go to the next place where the data is stored to read it. Okay? So the only way you're going to optimize this throughput is to minimize or eliminate seeks altogether. Okay? So how are you going to do this? The only way you can do this is write contiguously. Okay? I write one block, the next block is next to it. The next block. So I don't have any seek. I write to the next block, and I write to the next block, and I write to the next block, and so on. Okay? That is going to give you maximum throughput because only thing that the diskette is doing is writing. There is no seeking. So basically, it's only doing useful work. Disk seeks are not useful work. They're essentially useless work because there's no IO actually happening when you do this. Okay? So what does it mean to actually optimize writes in this fashion? You essentially think of your disk as a log. It's a contiguous log. You keep appending new data to the end of the log. Okay? So I start at the beginning because it's only write traffic, right? I take the next block that comes in, I say I write to the next location. Another block comes in, I write to the next location. So I keep writing. Okay? I get to the end. Okay? And then I might have to come back and redo this. Okay? So this is going to maximize output, not output, throughput. Is that clear, what I just said? If I write in a contiguous fashion, I'm going to maximize my IO. Okay? So I did this by writing in a log fashion. Okay? Now you might, as you can imagine, It's not like once you create a file, I never modify it. Okay? I might create a file, it got written to some location on disk. I open it up again, I modify it, and I write it back. Okay? In a normal disk, okay, normal file system, I would go back to the original location and overwrite those blocks. In this case, I am writing in an append-only fashion. So if I actually go back to where the file was written and modify it, I just introduced a seek because I was writing to the end of the block, end of the log, and you're saying go back there and change some data. Okay? So I will not want to do that. So every new write to a existing file actually writes to the end of the log. Okay? And I just have to mark that log, that block that changed in the middle as deleted. Okay? So I have a log where there are some entries in the log that are scratched out because those blocks got deleted and they got rewritten to the end of the log. Is that clear? So I will continue to write contiguously or sequentially. It's like sequential writes. I'm writing one after the other, but as data changes, I don't go back and overwrite it as I would do in a normal case. I just go to the end and keep it quick. Okay? Yes, question. Okay. Question is, how do you go back and mark blocks for deletion without having the same thing? I also write the metadata in a log-like fashion, right? So I can keep my super blocks in known locations and I can write them. Okay? So I could do that. I could also keep the metadata in my cache and flush them less frequently. Good question. But typically, even in a normal case, you don't go and write that to a block that I've deleted it. You put that in the metadata. I have a free block list. Okay? I just return that block to the free block list. That is how I'm going to say the block was deleted. I don't have to actually write to a block. Deleting a block means I add it back to the free block list. So file system knows it's not in use. It's available. Okay? Now, as you can imagine, if you have a log and you've done lots of writes to that log, you modified the files over and over again, you will have a sequential log, but it has lots of holes in it. Holes are where you deleted those blocks. Okay? And when the log reaches the end of the disk, I got to start from the beginning. Okay? Now, if I start from the beginning, I can't write contiguously because I have to go to only the holes and start writing them. Is that clear? Okay? But if I write to a hole and then I go to the next hole, I just reintroduce seeks. Is that clear what I'm just saying? Because I have holes, but now the holes are not contiguous. They're at random places based on what files have changed. So if I reach the end of the disk, I go back to the beginning. I can't do what I had started before where I'm just writing contiguous. I can only write to empty blocks which are at random locations. Okay? So that's going to reintroduce my seeks, which I don't want. That's what I was trying to avoid. So what do I do? You have to move the data. You have to do what's called compaction. Okay? This is basically garbage collection on disk. Okay? So you basically, that's what garbage collection in Java does in memory. It tries to go reclaim unused data. I have to basically go and do what is called compaction. Every once in a while, so I don't actually write one giant log on the disk. I have the disk into smaller pieces, not smaller, but big chunks. And then I make each chunk a log, and they're called segments. I'm writing a segment. I go to the next segment. I write them contiguously. So the goal has to be every once in a while, I do what is called disk compaction, like defragmentation. I run that defragment process. It collects all the data. I free up a contiguous set of blocks. I can write to them. Right? So that requires me to copy extra information. Okay? So this is going to add to some overhead because even though I am not writing as a user, the file system is making extra writes to compact data. So moving data is extra writes. Right? I move a block from one place on contents to one to the other, there's extra write. So whenever this compaction or garbage collection process is going to run, it's going to add to overhead. But hopefully it's not too frequent. Every once in a while you have to run this, but still adds to an overhead. Okay? But once you compact, I freed up a contiguous chunk. I can again write a new segment contiguously. Okay? So I need to make sure there are enough segments so I can continue my writing. Okay? And then make sure the holes are eventually defragmented. Okay? This is log structured file systems. Okay? So that is, so it was a nice idea. Okay? Not needed in world of SSDs. SSDs have no moving parts. Okay? I can go to, it's like accessing memory. Right? I just need a memory address and the access time is constant. It doesn't matter whether my next access to memory is the next byte or some other page altogether. It's the same overhead. So in the world of SSDs, you don't need this because you can write to random locations. It's going to give you the same exact throughput as if you're writing to contiguous. But in the days when you had disks with moving parts, this was absolutely a good performance optimization because it allowed you to improve your write performance. So this is a file system that's highly optimized for writes. Okay. Comes with some baggage, but you have introduced garbage collection, which no other file system has. No file system just randomly starts doing garbage collection, but this one has to in order to prevent, allow contiguous writes. Is this clear? Okay. All right. So with log structured file systems, now you have two concepts, and we are going to see how to essentially build back xFS. Okay. It uses two ideas. It uses RAID, and it combines them with log structured file system. Okay. So basically, I'm going to stripe my log. I write as a log. Okay. So all files are appended, and this log is striped across machines. Okay. So it's basically network striping. Okay. So I have this log segment. I basically make 4 blocks, a parity blocks, and then I just put those blocks on these. These are not disks, they're actual machines. These are disks on different machines. So I put the first block of the log on machine 1, second machine, third here, write the parity block. I can do the same thing like RAID 5 and so on. Okay. Every once in a while, I will have to look at my holes. I have to do garbage collection. All of that is still there. Okay. But I'm now optimizing for write traffic. There was a giant caches that make sure that most of my traffic is right. And I'm maximizing the storage on all the machines. So I get parallel IOs. Okay. The same thing we had for RAID. So I essentially have high throughput because I parallelized my IOs. Okay. And I've also reduced disk overheads of seeks because I'm striping and using log structured organization, which appends to the disk. Okay. So if you combine these two, you get xFS. So you see there's no server here. Okay. All machines in the system are participating. They'll store 1/n of the information. Of course, a machine dies, goes away. You have to get the parity, reconstruct that data on another machine. All of that has to be done. Okay. But so long as you do that, you are now saying, why not use disks on every user's machine? Why only use the disk on the server? Then I can get a lot more space for my files that collects all the storage space on all the machines and makes it like one big pool of storage. Okay. That is xFS. Okay. We have 10 minutes, so I have 2 more file systems to talk about, then we are done. Okay. Next file system, Hadoop distributed file system, HDFS. Okay. Now, if you're done anything, if you've done this course, what is it called? Systems for Data Science. Some of you may have taken it. So you probably heard of MapReduce or Spark. Okay. So MapReduce or Spark are frameworks that allow you to do large-scale data processing. Your large data set, you can use a cluster of machines to process them in parallel. That's the basic idea. Okay. So that's all you need to know as far as HDFS is concerned. Okay. So this is a file system that is designed for read-only operations. It's the exact opposite of LFS. Because if you think about how data processing works, your large data set. Okay. Let's say you're doing a machine learning training. Let's say you're doing something else. You will, whenever you want to train the model, you will read all of that data, you will train it. You're not modifying the training data set ever. It's mostly being read once you put it on disk. Okay. So in the world of high throughput data processing or AI machine learning training, okay, the disk traffic tends to be more read-only. It's the exact opposite of what we said in LFS. Okay. It's more read-only traffic. Okay. The data is so large that putting caches doesn't help a whole lot because the size of the data is far more than the size of memory on the machine. The terabytes, petabytes of training data. You don't have that much RAM that can put these caches and absorb all of the I. Okay. So you still have to optimize your disks for these operations. Okay. So this is a file system that is optimized for large data sets. It is designed more for reading than writing. Okay. Of course, it supports writes because you might have to store a new data set or results of your data processing, but there will be more reads in the system than writes necessarily. Okay. So how do you design file systems for this case? Okay, so you want to ensure that it's fault tolerant. You want to use batch processing. Okay, this is not designed for I open a file in my editor, I make some changes and I save it. That is not this kind of file system. It's saying, let's put 1 terabyte of data and read it and do something with it. Designed for very large file IO. Okay, so batch processing, not interactive processing. Okay, designed to scale to hundreds of nodes, hundreds of machines in the system. Okay, it has essentially worm model. Write once, read many. Is what I meant by it's rarely retry. Once you write large data set, you rarely change it. So you should assume it will almost never change. Okay, so if you want to do it, you can do some append or something like that. So very different set of assumptions. Okay? In fact, some of them are opposite of what we saw previously. Okay? Here's how it's going to work. Okay? So essentially, the main architectural principle here is you are going to have 2 types of servers in this file system. You are going to have what are called metadata servers, and you are going to have data servers. Okay? Metadata servers track where the data is stored. That's what metadata means. Okay? But since the amount of data is so large, you have special servers that only do metadata processing. They don't actually store any data. They store data about the data. So they will only keep track of where are the blocks stored, which files are stored on which machines, etc., etc. Okay? And then you are going to keep the files on the data nodes. Okay? Unlike previous cases, you are not striping in this case. You could if you wanted to. That's a separate matter. But by default, HDFS doesn't do striping, but it does replication. Okay? So because you're not doing striping, but you still don't want data to disappear. Okay? So you not only do mirroring, you store 3 copies of every file. Okay? So standard degree of replication in HDFS, factor of 3. Okay? The idea here is disks are cheap. Okay? It's fine to keep 3 copies of the file. Even then, I have so much disk that it doesn't really matter. Okay? Unlike when we said, I don't want to double my hardware cost. In this case, you say, I don't really care. You can buy for $100 1 terabyte disk. So why can I not keep 3 copies of it? Right? So every file is stored on 3 different servers. Okay? The metadata servers are tracking that. Okay? These are all large files. Right? So they're going to track where are the 3 copies stored. When a request comes in, maybe you can even load balance and send some traffic on some node, some other traffic on another node, and so on. Okay? So metadata servers track where the files are stored and how many copies. Okay? The data servers are essentially all going to store the actual file. You could add striping if you wanted to, but by default, you are storing files themselves and keeping 3 copies. Okay? So when requests come in, you are going to send them to the metadata server first, and then you're going to send it to a data server. So there are 2 servers that are going to be involved in every read request. First, to find out where the file is stored, and then go to the machine where the file is stored and retrieve it. Okay? The actual file system on each of those nodes is a normal file system. HDFS is a layer that sits on top. Okay? You can just run HDFS on Windows, NTFS, or Mac OS has its own file system, or Linux file system. Each machine is a standard machine. It acts like a Linux machine or a Windows machine. This is just a layer that sits on top that is distributing and replicating files. Is that clear? So you can run HDFS on existing machine. You don't actually need to change the underlying file system itself. Okay? The replication factor is configurable. The default is set to 3, but you could say, I don't want to do that. I want to set it to 1, and HDFS will not make extra copies. Machines die, the data is gone. Okay? But if you want, you can keep it at 2 or 3 or even more than 3. That's a parameter you keep, and then it will decide how many copies to create and where to put them. Okay? So that's not a set parameter. What I told you was kind of the default it will assume in a system. Okay, that's HDFS. Okay? Here's another file system, Google file system, GFS. Okay? Similar idea, okay, as HDFS, but this is using some slightly different ideas. It is designed for more general purpose access, not large data sets, but large data sets can also be used in this case. Okay? So essentially, very similar ideas. Okay? The file is divided into chunks. Okay? Chunks are going to be striped across machines. Okay? It uses network striping. Okay? So file has chunks, like just as blocks. Chunks are now spread across machines. That's what we did. Okay? But rather than computing parity information, so you are disk striping, so think of it as like RAID level 0. Rather than computing parity, you are using HDFS idea saying disks are cheap, let's store each chunk on 3 different machines. So replicate your chunks. Okay? So not only is it there are 2 copies, there are actually 3 copies by default. Okay? So you have same idea. There's a metadata server and there are data servers. Metadata servers say when a file comes in, how to create the chunks, how to allocate 3 servers to store each chunk, so that is replicated 3 times, and you track all of that. So when a read comes in, you can send that read request to any of the machine that have the chunks. Okay? So you can distribute your load traffic. Okay? In addition to that, is also going to do atomic writes, but by and large, okay, so what has happened here is you are using striping. So you load balance, like HDFS where files were individual, so you may have imbalances. Here you are going to load balance for your chunk servers and you stripe them. Okay? You keep all this metadata on separate servers, okay? And you replicate each of these 3 times. Okay? Again, GFS is a layer that runs on top of existing file system. The underlying file system here is just a standard Linux file system. So the chunks are essentially files. They just are given some random names, saying file 000 or chunk 000 is a file, okay, but it's actually a chunk of the Google file system. So if you open it, you won't see anything because it's part of some larger file somewhere. Okay? So rather than storing blocks, you are just storing chunks as files using a local file system. Okay? So these are all very large file systems that are used to scale to very large systems. Okay? So you can store lots of data. You can use it for doing all kinds of processing. You can store large data sets. All kinds of things can be done with this. Okay? So one more slide. I'm going to talk about it very quickly, then we'll end. Okay? So this is an object storage system, which is not a file system. Okay? Object storage systems are storage systems that are used by cloud. In AWS, you have something called S3, Simple Storage Service. Okay? That's the idea of an object storage system. In object storage system, your data does not have file names. They have handles. Okay? So you have a handle which you use to get your data. Okay? And the data is you can use, rather than doing reads or writes, you use what are called gets and puts. A put is similar to a write. A get is similar to a read. Okay? And you don't have a hierarchical namespace. There is no file names. There are no directories. Okay? There's just a large amount of storage. You can create what are these called blobs. Okay? They have a handle. You can go and get that entire blob out using gets or puts, or you can store data in. Okay? So it is not used. This is not a file system. Okay? It's essentially a storage system that uses what are called objects. So they are used for more like backups and archival storage and so. So you want to take a backup of a large system, you can put that whole thing as one object into an object storage system. Okay? And then you can get it back using gets and puts and so. So not hierarchical file naming in terms of directories and all of that. Okay? Just large scale storage, but does not use file system concepts. It uses object storage concepts where objects are just large blobs of data. Okay? They don't have names like file name, but they have handles that you can use. Okay? And the last and most important thing is you are using HTTP gets and puts to do this. Okay? You're no longer using file open or anything like this. So long as you have a handle, which is a URL, you just do an HTTP get and you can get your data. You do an HTTP put, you put your data back. Okay? So file names here are replaced with URLs, which are the handles. This is running on top of HTTP, but still a storage system. Okay? These are used for large-scale storage in cloud computing. Okay? You can go to Amazon using your test account and create an S3 bucket, and then you can use gets and puts to store data in, just as an example. Okay? So we are out of time. Actually, we are a minute over. So let's stop here. Okay? Next time, we are going to resume with a new topic. We're done with file systems today.